then I will show you this one. There, so there. Okay, now look at these. And I have to tell you, both sections have shown the same cast. For some reason, it does not show on your, but anyways, you can watch this. So this is a person who achieved in the class 96%. And this is the person at the bottom who has achieved 64%. And this is what shows, the Canvas shows in terms of time spent. And they have a unit here, 100. I don't know exactly what 100 means, but it's a unit. They say it's like contact hours. And it's not just staying there, as I've tried it also. It's not like opening it up and waiting idle. It needs to see activity, all right? So look at that. Look how it goes down to the lowest. Okay, it's so practically your performance in the class is directly related to how much time you spend in the class and nothing else. Even you may say, well, I'm in computer science and I have these kinds of, no, I mean, it does not at the end make so much difference because yeah, we use vector algebra, we do these kinds of things, but it's not like that we are using it in a way that you need to be proficient in that. So the fundamentals that we really are using are there for all of you, regardless of which courses you've taken or not taken, how you did in previous courses. This is minimal. What makes the difference in the class is how much time you spend. And then I want to show you something else, which I also found very interesting. So, and it's this one. Let me see. I had some other ones, but I think, okay. So tell me from these two, which one is the 92%? These are two students. One of them achieved 92%. The other one achieved 85%. So what do you think? What is your, all of you, from also those of you online? Which one?
B.
B is the 92%. What is the difference between B and A? It's what I tell you all this long time. Yes, and more consistent. I mean, the person, whoever this person is, because I need to tell you also, there are so many students, I don't remember names. I don't. And I looked through many of these. I don't know who this person is, but whoever this person is, even when we were down in power, even a little bit of time in this class, this person here, between this and that, this person here learned a lot more, even because this person spent a little bit of time compared to this person. So working in between, it does not need to be many hours. That's what I'm trying to tell you. Believe me in that. Manage your time successfully. Is what you do. If you do a little bit every day, you're going to be way better if you spend an enormous amount of time just in chunks of time that are separated. Because that is like, we are engineers, all right? It's like you have a computer. If I come to you with a computer that has less memory with another one, are you going to try to take the computer with the less memory and try to run these parallel programs? You're not going to do that because you know what the computer cannot do. Our brain is like that. Our brain can do some things and it cannot do other things. And if you see how the brain works, it works with neurons, and the neurons have synapses. And the brain does not have a lot of memory to store everything like this computer. It does not have that capability. So the brain is smart. Evolution. What did the brain do? The brain only uses information if it gets repeated opportunities to revisit it. So if something comes here, one piece of information, and I don't see it again, the brain places at some point in temporary memory, and then it erases it because you need space for something else. So you have to recall information regularly to be able, and then if you do that, even with a very short period of time, you recall that, then the synapses that connects your processing units there to whatever this information is gets stronger physically. It's a chemical computer, right? And that's what happens. So you use your brain the wrong way. You're using it for something that the brain cannot do. And that's what you need to remember that. At least remember this, if anything else, from this class. Because you're going to be better, more effective in your work without killing yourself, compared to others who don't do the right thing and they kill themselves, and that they will perform worse than you will. So that's what you need to keep in mind, right? I just wanted to show you the data here so you can remember it. Other than this, I wanted to also suggest, and now we are going to then go to our class. I wanted to suggest that for those of you who received grades that were lower, I think I would like you to come and see me so we can develop a program from now on, a plan at least. Let me call it plan. We are going to develop a plan because it's going to be a mistake after you spend this much time in class not to get out of this class with a good grade. All right, so a plan is needed for some of you. And I have those of you who I said, please come and see me, then make sure that you come and see me. And I'm not going to ask you, why did you not do that? I'm going to ask you how I can help you from this point on. What is it that I can do to help? So out of this class, you get a grade that makes you satisfied. Not me, all right? You, yourself, okay? Sounds good? Any questions? Yes. I have not looked at the average, but I have to tell you, probably is around 110 out of 200, 120. How much is it? Because I did not look. Yeah, maybe 120, I think. Okay. So what we will do here is now we are going to continue after I said that. And I would like you also to share your thoughts with me. Maybe at that point, I need to pause a little bit for a few minutes. Tell me, if you were to give me advice for next time, what would that advice be in preparing you for a midterm or creating a midterm? Yes. Okay. So the timing is good. But I'm going to send you another. I know it's very difficult for somebody who may have a little more critical, all right, to say that. I would not. If when I were a student, I would not speak out because, you don't do that. I was not doing that. So I understand that. I will send you, not immediately, but like in a week, another survey. And you're not gonna change the grade, obviously. You have an opportunity, however, to help me to change what I'm doing. Because the goal I have right now is to get you to learn as much as you can, and then for me to assess your learning and hopefully in the process to get out with good grades. All right, so that is, and I wanna make sure that I don't waste your time. When you come into this class, you come to learn something. You have a profession to go to, you have things that you wanna do in your life. I wanna support you in that. And I wanna make sure I don't waste your time when you come to class and say, well, who wants to go there? I don't wanna do that. All right. Having said that, now I'm going to share the other screen and continue today with the inductance concept. And let me, from there, just 1 second. Okay, we have seen those things, this information here. I just want to clarify a couple of things which I believe will be important, especially since we have seen that. And then I have also a couple of examples that hopefully we can go through one, and then I would like you to read them. The solution of the examples is very extensive, and I would like you to read it. But I have to tell you one thing. The fundamentals are extremely important. I know that you are very anxious to go into examples. Examples are good if I give you the same thing. So I can go into examples without talking about the fundamentals. But if I change something in an example that you have already seen, then you're not going to be able to even address it. So the fundamentals, I know sometimes for some people think it's a waste of time. And that's why we have office hours, and today I will solve problems as we do every Wednesday. But I wanted to remind you that understanding what we are doing is extremely important. So this is an example right here in front of us, where we try to find the inductance of a single loop. All right, so you see that the loop has one current, I, here. And this current, if you use the right-hand rule, in fact, I can increase that a little bit. If you use the right-hand rule, you will see that the field inside, all right, because that's what we care about, is the field that goes inside the loop. Everything that goes inside the loop, all of the sections of the loop, if you were to take that loop and then split it into tiny pieces, all right, so practically you have all of these currents, all of them, running around the same direction. Each one of them inside the loop is going to create the same direction of the field, because that's what comes out from the right-hand rule. So if I use this for the front current that is towards me, for this one, for the front current, then it shows that the magnetic field goes from under, through the loop, going upwards. If now this way is my the thumb now, I have turned my back, all right? My thumb now shows the current at the back of the loop. And then my hands, my other fingers, show the direction of the magnetic field through the loop. Also, it goes up, from under up. So what happens inside the loop, all of the magnetic field lines go along the same direction, which means all of the small currents that I can consider, they all create a magnetic field that has the same direction, and therefore you can sum it up. And that's why the field inside the loop is the strongest. The moment I go outside, all of the currents, so if this current outside the field is going to turn like this, going down. While for other currents, the field is going to still going up. So outside of the loop, the lines do not align, all of the lines. So they subtract, and that's why we have this kind of distribution, as you can see here, is strongest inside the loop, and it quickly goes down outside. Now, ideally, well, in reality, this curve is not exactly flat. It does not make ripples or anything, but it's like a small hill. All right, you can think of a hill like this. And most of the time, people will assume, if they want to find a closed form formula for the inductance, that the value of the total magnetic flux density on this loop, they assume, is approximately the same with the value of the magnetic flux density that is here at the center of the loop on the loop. All right, because that's where we get, this is the magnetic flux density that is important if we want to evaluate, if we want to calculate the inductance. The inductance, according to this formula here, is the ratio of the total flux through the loop divided by the current that flows through the loop. So we want to find the flux through the loop. How do we find the flux through the loop? We practically go on the surface of the loop. We find all of these arrows show practically the magnetic flux density on the loop. We assume that all of the values of these arrows are the same and they're the same value with the magnetic flux density at the center of the loop. So we get that value which we calculated, all right, before. And then we multiply by the area of the loop and we simplify things. So at the end, what you find here is if you have a loop that has a radius of A, then the inductance of this loop is pi mu naught, which is like in free space, all right, the magnetic permeability times A over 2. And this is exactly what we find for this inductance. Okay, so now that we have done this, we think of the following. Let's assume that you have now multiple loops. You remember the problem we did with two loops that were one loop on top of the other, and then they, in one case, they had the same direction of the current. What if I have 1, 2, 3, 4, and so forth? Many, many loops, but they are tightly close to each other. Practically, you see that the magnetic flux of each of these loops goes through all of them, all right? You see that? And that's this situation where the magnetic, loops come so tightly to each other is what we have in coils. Have you seen this in the, well, there are two types of coils, probably you have seen. Have you seen coils like inductances in the lab? Large inductances, they have to look like coils, all right? So like it's like one wire that you wind tightly around the core. But if you have not seen those, because sometimes the inductors are tiny, you don't see inside how they look. Have you seen the inductors we are using in the power lines? Have you seen them? Have you heard at least about, forget about the inductors, how about like transformers in the power lines? Okay, when something blows out and then you hear a noise and then your power goes down, what is happening? One of the transformers is damaged. So what happens when a transformer is damaged? You just have a material breakdown, all right? So it's like there is a small explosion of some sort. That's how it sounds. These transformers, they're nothing else but two coils. There is a very high density core that is iron most of the time. And then they go and they wrap around this wire so tightly, so practically one loop is next to the other, all right? In that case, when that happens, because there is a current that flows in its loop as you wrap around the wire and creates a loop around the core, then each of these loops creates a flux, which is the integral of the magnetic flux density on the surface of the loop. And then as you bring the loops together, what happens to this flux? It goes through all of the loops, and therefore the flux that is created by each one of these loops goes through all of the loops. So practically, you see here that if you have one loop, and you look at the flux through this one loop, let's assume that this one loop is J, all right? So the total flux through this one loop here is the sum of all of the fluxes that are created by the other loops. So in that case, the total flux from one loop is equal to n if their loops are identical, all right? The number of loops times the flux that goes through, that is the flux of one single loop. I call that psi naught. Okay. So what happens then, look at what then happens down here. When you have all of these loops, one next to the other, and each one of these loops has an inductance. If, say, for example, I could for a moment forget about these other loops, all right? I take only one. I know that the total flux through this one loop is equal to the n, the flux of each one, or to the sum of the fluxes of all of the other loops, plus that one, all right? So it's n times the flux of a singular isolated loop. Now, that is the inductance of the first coil. I go to the second coil, I find the inductance of that. I go to the third coil, I find the inductance, the third loop, I find the inductance of that. And then I go to the last loop and I find the inductance of that. All of these inductances are in series. So the total inductance of this combination of loops, which is nothing else but the coil rather, is the sum of these inductances. All right, so the total inductance here is the sum of these inductances down there, which in fact tells you that at the end of the day, the interesting things about a solenoid is the inductance of the solenoid is n squared the inductance of a singular isolated loop. That is very important, and that's why we go and create large inductances, inductors, using solenoids, because we have the n squared. Now, if in addition to n squared, I go and put a core in there, do you see how I wrap around this wire around this core? Usually the cores are very highly magnetic materials, like iron, for example. If a core is like highly magnetic, then mu is in the order of many, many thousands or tens of thousands, 50,000, 80,000. So now, if you put this core, if you have many loops in the coil and you have a core which is highly magnetic, then you create inductances which can be 6 orders of magnitude, 8 orders of magnitude higher than a single inductor, which is one single loop. So that's how we make inductances for power, because we need to be huge. In fact, an inductor, I don't know whether you saw that, but I had, when I came from Greece many years back, my father had bought me something as a gift, but it was running on 220 voltage. And I needed to get a transformer that goes from 120 to 220, all right, to use it, because I did not, it was like a personal thing. I mean, I did not want to throw it away. It had no value, but it had emotion, emotional connection. When I got the transformer, it was this huge. Probably it's like 10 pounds. And the whole thing is a coil. You can see it. I mean, it's a coil. To do a transformation of 120 to 220, 110 to 220. And it's like maybe it's 10 pounds. I think when I hold it, I have to hold it with both hands. And it's like this big. So how do you think, why is it so heavy? Because the core is iron. And maybe something more than that. I don't know, it's huge. I'm telling you, it's like this big. Maybe what is that, like no, it's like half of a foot on the height, and maybe another 3/4 of a foot long, and maybe 10 pounds. That's to take 120 to 110 to 220. Inductance. The whole thing is an inductance, nothing else. You know how it is, transformers, all right? 2 inductors rather. That was the whole thing. And then they make it like that. It's very interesting, as a matter of fact. I don't know whether, if you guys next time do something like that, pay attention to what you buy to see. It's very interesting because we are using these things in everyday life. We just don't see them. That's what is happening, especially because you need a lot of power to come through, all right? You need a lot of current. That's why they have that. Otherwise, if you go like the small transformers, when you did a very little current, and then you have all of these, there are transformers in here because you use them here, you use them in Europe, all of the electronics, they're tiny, don't even see them. But the current is like what, microamps? But here you need a lot of current. So the inductors are pretty big. So that's how, in fact, the reason we developed those. Now, the toroid is nothing else than the solenoid, but instead of being straight, it's like round. And why it is better to have a round thing or even like a loop thing? Because in the solenoid, you go in from one side and you come out from the other. You see that you have the input of the current and the output are separated physically. And it's not very useful, all right? So a lot of times you're not gonna see a solenoid sticking out like that. You're gonna see mostly for transformers or for large inductors, you're gonna see something like that, which allows you the input and the output currents to be next to each other. And that's the only difference. And if you look at the expressions then you get, in this particular case, which is the solenoid, the total inductance here is gonna be an expression that has mu, obviously, has the square of the number of loops, n square, has the area of each loop, of course, it's pi a square, and then divided by the length of the solenoid. So now the toroid is exactly the same, but instead of length, it has the perimetry of the circle. Rather, it has the perimetry of this circle, which is right going through the center axis of the toroid, which is 2 pi b. So if you put 2 pi b there, then that's what you come with. All right, so L, the equivalent 12 for the toroid. If L it was for solenoid, for the toroid is this one. Oops. There. All right, so this is how about that topic. And then I would like to go to this one because that shows something that is very interesting to keep in mind. So this is an example. What does it say here? Here it shows a core, magnetic core, that is not a closed circle. Just it breaks on the right side. It has an air gap. And on the left side of it, it has a coil. It's like kind of a solenoid. It's not a toroid because it does not go all around, but it's kind of a solenoid, but around the core, around a circular core with a gap. And then it gives all of the dimensions. It's the radius of the core of this core. It's also the cross section of the core is like a circle, all right? The radius is 3 millimeters in this particular case. The material is iron, so it's 210 to the 5, very high. 10 to the 5 by itself is 100,000. 2 times 10 to the 5, and that's a mu sub r, is 200,000. That's what iron has, all right? That's why they put iron, which is very heavy. They put it for the core. And then we have here a coil, you see that? And then that is connected to a resistor and goes through a voltage. And the resistor is there, so there is a current, all right? You put a voltage, then you have a current that flows through, and then you have a resistor there, R. And then length of this kind of a solenoid is about 6 centimeters. All right, and then it says here, find the magnitude of the magnetic flux density in the core and in the air gap. So first of all, let's talk about this. We have here the solenoid. We know that each one, as we discussed before, each one of the loops of this solenoid is going to experience the total flux from all of the loops. All right, we just said that. That because the current is the same one and goes along the same direction on each one of these loops, then the flux from each loop will go through all of the loops. And that is going to happen with all of the loops. So all of the loops will see the sum of all of the fluxes. All right? So that is going to happen here. So the magnetic field, if we look in this area, is going to go. So that goes, let me see, I have to be careful. So it goes like this. Okay, so we'll go like that. All of the magnetic field lines, but let me, before I go there, inside here, will go like this. Okay. What is going to happen after the magnetic field lines leave that coil? Are they going to go like this? What do you think? So we lose the flux? That has a mu sub bar here, which is how much? 200,000. Okay? Now, let us remember to make a decision, to make it up our mind whether the flux lines will, whether my flux is going to leave the coil. So I'm creating a lot of flux here, which is important for inductance. But if I wanted to pick the flux from another place, what if I have lost it all? Then what's the point of doing this, all right? So now the question is, if I were to go here with another coil like this, am I going to see any flux going through this coil? Am I going to pick any flux? Because if I pick flux, then I can have a current on this other location. That's what transformers do practically. How are we going to make that decision? Any suggestions before I explain my thoughts? What do you think? To decide what is going to happen, we need to remember the boundary conditions. I will write them here. Let me remind you the boundary conditions. All right. What did we learn? Let's assume that I have an iron underneath here. This is iron. Mu sub bar is 200,000. And this one is air. So air here, iron here. And now we have a magnetic field. And the magnetic field, it's coming this direction. Magnetic field is coming this direction, all right? From our coil. This is the coil that created. Okay. And is inside the coil, but it is inside the iron, but it's now the coil stops. So the magnetic field comes here. Okay, that's H. Magnetic field can be either H or it can be B. What have we learned from the boundary conditions? That if you have an air magnetic interface, Remember we did that. I will do it here. If we have an air magnetic interface without any current flowing on its surface, this is the surface, this is the iron underneath it, and then it's air. If there is a magnetic field, then there is continuity of the magnetic field intensity along the interface. So if the magnetic field is continuous along the interface, that implies that if I have my lines, magnetic field intensity now, remember what I said, magnetic field intensity, I don't mean to do that. Okay, it's this one. Okay, if this is my magnetic field intensity, H, the boundary conditions say that along the interface, this H inside the magnetic material iron and just outside in the surface is not going to change. It's going to be continuous. The value is going to be the same as you cross the surface. All right, that's what the boundary conditions say. So this is H1, and if this is H2, and let's assume that this is, for example, the x direction, H1 tangential to the interface is equal to H2 tangential to the interface. That's what the boundary conditions say. Okay, that is H. What happens with B? If this is the case, then B2 here and B1 here, how are they going to look? B2, which is mu R, mu naught, H2, and B1, which is, let me do that, mu naught, H1T, it implies that B2T, T means tangential, is going to be mu sub R times B1T on the interface, which means B sub 2 inside here, B, here, will be 200,000 times, this is 2, then B here. So B2 will be 200,000 times B1, right at that point. And B2 and B1 will both go this way. So practically your flux remains inside the material. All of your magnetic flux stays inside the iron. So you're not going to lose anything. So practically that tells you that in terms of B, which is what matters for inductance, all of your B lines will stay here. They will all be here and everything will be almost zero outside, because if inside the iron my B is 200,000 times than outside, it's like the outside does not exist. So practically this B is gonna go around. The question is what happens at the air gap? Will it come to this air gap here and then it will go like that? Do you think I'm gonna lose it here? In this particular case, the air gap, if it's small, all right, we're not talking about air gaps that are big, but if the air gap is small, the lines, now again, boundary conditions. What we found in the, let's talk about this, the question, we're gonna put a question here, all right, and see whether this is happening. Let's go to the boundary conditions. What we were told now from the same boundary conditions is that while the tangential component of the magnetic field is continuous through the interface, and therefore the tangential B is discontinuous, the normal B is continuous through the interface. So if I had at some point, if I stop this iron, That's what it means. If I go here, and I stop the iron, I create a gap. The magnetic field, the magnetic flux density is not gonna do anything. It's gonna just keep going because it's gonna continue through this since it's normal. And if the gap is not very big, so you start losing it in free space, it's gonna enter the other side of the air gap. So all of the magnetic field lines will continue like this if it's a small air gap. So that's what happens here. So we're not going to look. Yes, go ahead.
So what happens if it's like a large air gap?
For a large air gap, things may become more complicated. If, for example, I go here, let me draw something else. Let's assume that I have now a rod of iron, okay, like the other one. And it was around like this. But then, and it was like that, something, all right? But then I create a very big gap. So if I create a very big gap, which is like a big part of here, of this structure, then the field lines will come like, will try to continue, will go, oops, like here. The magnetic flux lines will come like this. But then if there is no enough material to enter, at some point they are going to divert. All right. And yes, they're going to be here, but you're going to capture a smaller part of the flux. You're going to lose flux here. So if you want to create a gap for some reason in this, and you create a gap for all kinds of reasons, all right? Because you want to enter things, because sometimes you create those gaps because you want to move something. You know, if you have a very strong magnetic field and then you have an alternating current, you create a motor. You remember that from physics? Well, you cannot have a very big gap. If you want to create a motor, you have to have something that is moving, so you need to open a gap. But if the gap is too big, you're going to lose part of your flux. It's going to spill over. So your gap has to be as narrow as possible to preserve your total flux. Yes. So here, according to this, it says here, find the magnitude of the magnetic flux. So you find this from the previous one, all right? The total magnetic flux here. You find it from the solenoid problem that we solved before, so we have that. So if you go to the solution, you use the results from the solenoid. And then you say that it continues through the air gap, as it says here, for the reasons I explained. All right, so the small air gap is not going to do anything to it. And as I said, if you want to put something, and then so according to this, using the solenoid formula, we find here that the inductance is 0.118 henries, which is huge. If you think that in all of the circuits what we have nanohenries, that kind of inductance we have. All right. Now, let me go back to the initial. And I know that the time is coming close, so I'm going to ask you to think about it. And then as you look at the problem, let us look at this coil. If N is not very large, if the number of loops in the solenoid, in the coil there, is not very many, and then you just wrap it around a core, the loops are not going to necessarily be all very close to each other. So we cannot use the solenoid formula where we assume that you have all of these loops running over a short length. if you have 10 loops here and they are somehow you wrap it around, but you don't put one next to the other, that formula that we use is not necessarily correct. It's like when the loops are away from each other, it's as if you have an individual loop, many individual loops in series. And in that case, what you would have to do is not to use the formula for the toroid for the magnetic field, but to use the formula for the magnetic field for a single loop. Now, if those are all around a high mu core, you're not going to lose your flux, obviously, but the magnetic field density inside this coil is not going to be what we found from the solenoid, where you have 100 loops in a short distance. If you have only 10 loops in the same distance, then this formula for the solenoid does not apply anymore. And in that case, what would I do? In that case, what I have here as approximation 2 I use as function of B, as expression for B, which B is the magnetic flux density through one loop. I use what we found, this is the first, the first one. I use what we found for here. Of course, for a single loop, it would be mu naught I divided by 2a for one loop, all right? But then you have all of these loops, and then the flux from each loop goes through the core and then goes through all of the other loops. So practically the total B is going to be n times that. And then that gives you, and then you continue the same way, and that gives you the formula that you see here. But if you had, in approach 2 is when you have a very high density between the loops. So the loops is like one touching the other almost. Then we use the expression for the solenoid, which does not have a 2a, does not have a function of the radius of the core or of the radius of the loop, but it has the length of the solenoid. In that case, you get a different value for the inductance, which is like 0.59 Henrys. Why did I want you to see these two approximations? They're both approximations. They are not accurate, all right? These are approximations for us to do like an order of magnitude kind of a design, if you like. They tell you that you're gonna be somewhere between half and 0.1 of a Henry. They're not going to give you wrong orders of magnitude, wrong, obviously, but they're not going to give you the exact value. If you want to have the exact value, then definitely a company that does design for an inductor will have their own models, all right, to run this. They will have their own ways, not this kind of simplicity. But this is to give you a lot of times to show you that even approximate formulas will give you good approximations within an order of magnitude. And sometimes this is good enough, all right, for some like designs. So this is an example, one, and then the second you can see it's a very similar thing. Then I have two coils here. It's like two coils around the same, and then it's a square here. They, I don't know why I have shifted a little bit. I will fix that, but there is a square here core, and there are just two coils that are around it. And it asks you to find, says, assume that there is a steady current goes through the points, find the inductance of this toroidal as in between points 1 and 2. So it's the inductance of this plus the inductance of that. And then what happens if the size of, that's an interesting one. Look at this, and maybe we can discuss a little bit that before we start next week on Friday on transmission line. What happens if the size of the iron loop changes? So 10 centimeters becomes different, but the solenoid, the number of the loops remain the same, but the size of the solenoid changes. That's kind of interesting problem, all right? Think about the last, which I don't have the answer here, so I can talk a little bit about that like 5 minutes before we start next time. you need to think about which of the formulas you're going to use and whether, in fact, look at this, approach 1 and approach 2 here. That is going to give you the answer of which of the two depends on the length of the solenoid, but not on the number of loops. That is going to tell you which of the formulas is more sensitive to the length of the solenoid, all right, than the number of loops. So in any case, this shows you a little bit on how we get these approximate expressions. Don't believe that they are accurate exactly to the point. They're giving us an order of magnitude of a value, but they're good enough for some approximation, some simple designs. So that's what I wanted to say. And now we have practically identified two things we need to remember: capacitance from electrostatics and inductance from magnetostatics, and how these two will be extremely important together with resistors, resistances, and resistance is like an ohmic conductor, all right, where there is a current that flows through, and then the electrons become excited. We'll talk a little bit about that. We'll review it again in transmission lines. You have resistances, you have inductors and capacitors, and the three elements are the fundamental components of a transmission line when we try to understand how a transmission line works. Also, we are gonna talk about some things you have seen before. We're gonna start with that on Friday. But that's what is the end of the magnetostatics, and you will see the sections that we are covering from the book. If you go under week 10, you will see exactly which sections we have covered from. There are very few practically, because there's so much more on magnetostatics that the book has. Any questions? The last thing, I will activate one top hat example exercise. Is very simple. Think before, look at what you see here before you start that. Remember that an inductance mostly depends on what? Like the capacitance. The inductance has an expression that does not involve what? Current. Remember that? Inductance only depends on the geometry. Capacitance only depends on the geometry. Whether we see a capacitance in a circuit, the value of the capacitance, when we see the inductance depends on how we excite them, but they exist there. So when you go to the lab and say, go and pick up a 3 nanohenry inductor, you don't have it's an inductor, it's there in the bin. All right, people have made it. It does not have a voltage around it, but it's an inductor. So they have created an inductance. How you use the inductance in the circuit and how you excite your circuit, that's a different story. But capacitors and inductors and capacitances are elements, they're fixed elements. Capacitances and inductances are properties that are independent of the excitation. But how they impact your circuit, that's a different story. And the impact of this on your circuit depends on the excitation, all right? Okay, we're gonna see those more in transmission lines, but you need to keep that in mind when you do the top hat problem, which I'm gonna activate now. Any questions?
So we were discussing the two ways of solving for the inductance of the shaper. So you said one of them was like the way with the solenoid, and the other one was like related to the toroid.
Yes.
Okay, and so what did you do again to like determine which formula you use?
Well, they're both approximate. Really, they give you a range. They don't give you an exact value, but they give you a range. They tell you this is the lowest value you can get, and this is the highest value you can get. So you can use both approximations to find the range. But they give you more or less an order of magnitude kind of thing.
So one of them is like a lower bound equation and the other one's a higher bound?
Yes. One gives you the lower bound, the other gives you the higher.
Which was lower and which was higher?
Well, it depends on the length of the coil in relation to the diameter of the loop. So usually those loops are much smaller in the diameter than they are in the length. So usually the one that has the length gives you underneath in the denominator, which is the solenoid, that gives you the lower bound. And the one that has the radius of the loop in the denominator gives you the higher bound.
Okay.
Okay.
Thank you.
All right, you're welcome. Okay, so I will see you this evening. We're going to solve some more problems, and otherwise on Friday. You're welcome. And